21.76 micrograms. That is roughly a grain of fine sand sitting on your fingertip, small enough to lose, large enough to see. It is also, according to one of the most decorated physicists alive, the weight at which the universe stops permitting maybes. Below it, a thing can be in two places at once and simply stay there. Above it, something steps in and settles the matter. No observer, no measurement, nothing watching at all. If that is true, then the definiteness of everything around you, the plain fact that the cup is on the table and not also on the floor, is a physical process with a clock running on it. And it means the version of quantum mechanics printed in every textbook you have ever seen is missing a piece. Physicists know the piece is missing. They have known since 1926. It is not hidden, it is not controversial, and they teach it to undergraduates. So why does almost nobody work on it? Settle in. Subscribe if you haven't already and stick around, because the answer runs through a grain of sand, a Nobel laureate insisting the entire field is facing the wrong way, and a machine under a mountain listening for the sound reality makes when it decides. Let's get into it. Part 1. The quietest place on Earth. There is a motorway that runs through the mountains of central Italy, east of Rome, cutting under the Gran Sasso Massif in a pair of tunnels almost 10 kilometers long. If you drive it, you will not notice anything unusual. You will go into the dark, your radio will die, and about halfway through on the right-hand side you will pass a set of doors that look like a maintenance bay. Behind those doors, under roughly 1,400 meters of solid limestone, there are 3 enormous halls carved out of the inside of a mountain, filled with some of the most sensitive instruments human beings have ever built. People go to a lot of trouble to build a room like that, and it is worth understanding what the trouble buys. Right now, standing where you are being rained on. Not by water, by cosmic rays, the shattered remains of particles that were accelerated somewhere out in the galaxy, slammed into the top of our atmosphere, and broke into showers of secondary particles that arrive at the ground constantly, everywhere, day and night. Several of them are passing through your body as you listen to this sentence. On the surface of the Earth, that rain is a background hiss you simply cannot switch off, and if you're trying to detect something incredibly rare, the hiss will drown you. Rock absorbs it. Not perfectly, but very well, and the deeper you go, the better it gets. Physicists measure the shielding of an underground laboratory in a slightly strange unit, meters of water equivalent, meaning how much water you would need to get the same effect. The Gran Sasso Hall sits under about 3,600 meters water equivalent. That is enough to cut the cosmic ray flux by a factor of about 1 million. It is, in the most literal sense available to us, one of the quietest places on Earth. And inside that quiet there is a tank. It is called xenont, and it contains about 8.5 tons of xenon, cooled until it is a liquid, of which roughly 5.9 tons make up the sensitive part where the physics happens. Xenon is a noble gas, which means it does not want to react with anything, which is exactly why it is useful. It can be purified to a degree that borders on obsessive, with radioactive contamination measured in parts per trillion. Around that tank, staring inward into total darkness, sit 494 photomultiplier tubes, each one capable of registering a single photon of light. The whole apparatus is a machine designed for one purpose, which is to sit perfectly still in the dark and notice if anything at all happens. What it was built to notice is dark matter. That is the thing you have probably heard of. The invisible stuff that seems to make up most of the mass of every galaxy, including ours, holding the spiral arms together against speeds that should have flung them apart long ago. Nobody has ever caught a particle of it directly. The hope, with a machine like this, is that one of those particles will eventually clip a xenon nucleus, knock it sideways, and produce a tiny flash of light and a puff of freed electrons that the 494 eyes can see. That is the headline job. It is why the money was spent and why the mountain was drilled. But a detector that quiet is useful for more than one question, and this is where the story turns. Between the 6th of July and the 10th of November 2021, Xenont took its first run of science data, a period the collaboration calls SR0. When you strip out the outer layers of xenon that act as shielding for the innermost region, you are left with a working mass of about 4.37 tons, and over those 4 months the experiment accumulated an exposure of roughly 1.16 ton years. That number is the currency of rare event physics. It means 1.16 tons of ultra-pure liquid xenon, watched continuously for 1 year's worth of total observation. And a group of physicists went through that data looking for something that had nothing to do with dark matter at all. They searched the low-energy electronic recoil data in the range from 1 to 140 kilo-electron volts for a very specific signal, a faint, structureless whisper of X-rays coming from the xenon itself, not from radioactive decay, not from anything hitting it, from cold, ordinary undisturbed matter sitting in the dark for no reason at all. Standard quantum mechanics says that whisper does not exist. Cold matter, left alone, does not spontaneously emit X-rays. There is no mechanism for it. The prediction is exactly zero. So they were not testing quantum mechanics against a rival experiment. They were testing quantum mechanics against a rival version of itself, a family of theories which say that the textbook is not quite right, that something is missing from it, and that the missing piece would leave a fingerprint. If those theories are correct, every atom in that tank and every atom in you is very faintly glowing all the time and always has been. On the 23rd of March, 2026, the result appeared in Physical Review Letters, Volume 136, Article 120201, under the title Challenging Spontaneous Quantum Collapse with the Xenon Dark Matter Detector. They did not see it. And I want to be careful here, because a null result sounds like a non-event, and this one is anything but. Not finding the glow is the measurement. It puts a ceiling on how strong the effect can possibly be, and that ceiling is now dramatically lower than it was. For one of the two main families of these theories, the bound tightened by 2 orders of magnitude, a factor of 100. For the other, the one that will occupy most of tonight, it tightened by roughly a factor of 5. And for the first time in the history of the subject, the specific numbers that one of these theories' original inventors wrote down, back in the 1980s, as their best guess at how the universe works, those numbers are now experimentally excluded. Not disfavored, excluded. Somebody's guess about the deep structure of reality was checked, under a mountain, by a machine built for something else, and it was wrong. Now, here is the question that ought to be forming in your mind, and it is the question this entire video exists to answer. Why would anyone do this? Why would a team of serious physicists take one of the most expensive and delicate instruments on the planet, an instrument built to solve one of the great outstanding problems in cosmology, and spend a chunk of its first science run hunting for a glow that the standard theory says flatly cannot be there? You do not do that because you are curious. You do that because you think there is a hole in the standard theory. And there is. There is a hole in quantum mechanics, the most successful, most precisely tested, most thoroughly confirmed physical theory that human beings have ever produced. And it is not a small one, and it is not hidden, and it is not new. It has been sitting in plain sight, printed in the opening chapters of undergraduate textbooks, for very nearly 100 years. Physicists know about it. They teach it. Some of them can tell you exactly where it is on the page, and then, for the most part, they close the book and get on with their day. That is the thing I have never been able to let go of. Not the hole itself. We will get to the hole, and it is stranger and simpler than you might expect. What I cannot let go of is the looking away. Because these are not incurious people. These are the most relentlessly curious people our species produces, and there is a crack in the foundation of everything they do, and the overwhelming majority of them have made a quiet, deliberate, professional decision not to look at it. By the end of tonight, I am going to give you a straight answer as to why. It turns out there are 5 good reasons and 1 bad one, and 4 of the 5 have quietly stopped being true in the last few years. But before any of that can make sense, you need to see the crack. And to see it, we have to go back to 1926 and to a piece of mathematics that almost everybody agrees is the most beautiful thing in physics, and to the small, awkward, unexplained rule that has been sitting right next to it ever since. Part 2. The 2 rules. Open any undergraduate quantum mechanics textbook, any of them, in any language, from any decade since about 1930, and somewhere in the first 100 pages you will find 2 rules for how the world changes over time. They sit side by side. They are usually introduced within a chapter of each other, and they have almost nothing in common. The first rule is the Schrödinger equation, written down by Erwin Schrödinger in 1926, and it is, by any reasonable standard, one of the most beautiful things anyone has ever discovered. What it does is simple to state. It takes the quantum state of a system as it is now, the wave function, the mathematical object that encodes everything the theory has to say about that system, and it tells you what that state will be later. If you know the wave function at this moment, the equation gives you the wave function in 10 minutes and in 20 minutes, and tomorrow and next year. It is a machine for turning now into later. 4 things about that machine matter tonight, and I want to lay them out carefully, because in about 5 minutes, I am going to show you a second rule that violates every single one of them. The first thing is that it is smooth. The wave function does not jump. It flows continuously the way water flows, with no gaps and no sudden steps. The second thing is that it is deterministic. Given the state now, there is exactly one state later, not a probability of several, one. The equation contains no randomness at all, which surprises people, because quantum mechanics has a reputation for being the theory where God plays dice. And this, the central equation of the whole subject, is as rigidly deterministic as anything Newton ever wrote. The third thing is that it is reversible. Run the equation backwards and you recover exactly where you started with nothing lost. Nothing is destroyed. Every bit of information about the initial state is still there, in principle, forever. There is a word physicists use for the first rule, and it is worth knowing because it will come back. They call the evolution unitary. What unitary means, in plain terms, is that the total probability always adds up to 1 and nothing ever leaks out. No possibility is created from nothing, and none is quietly deleted. It is a conservation law for the bookkeeping of the world, and it is precisely what collapse violates. That same violation, in a completely different costume, is what makes the black hole information paradox a paradox. The question of whether anything can ever truly erase the past is, at bottom, the question of whether unitary evolution is exceptionless. Hold that thought lightly. It will not come up again tonight, but it tells you how deep the crack runs. And the fourth thing is the one that does all the damage. The Schrödinger equation is linear. What linear means, stripped of the mathematics, is this. If the equation permits a state in which a particle is over here, and it also permits a state in which that same particle is over there, then it necessarily permits the sum of those two states, here plus there, both at once. I want to sit on that for a second because it is routinely explained backwards. People often talk about superposition as though it were a weird extra feature that quantum mechanics bolts onto reality. A strange claim the theory makes about particles being in two places. It is not an extra feature. It is a consequence of the shape of the equation. If you want a theory in which the states add together like waves, and you do want that, because that is what produces every interference pattern anyone has ever measured, then you are stuck with superposition. It comes free with linearity, and you cannot have one without the other. So that is rule 1. Smooth, deterministic, reversible, and generous with possibilities to the point of absurdity. Now here is rule 2. Rule 2 has no equation. That is not a simplification for a general audience. It genuinely does not have one. It is a recipe, usually called the collapse postulate or the projection postulate, and in words it says this. When a measurement occurs, the wave function abruptly jumps into one of the possible outcomes. Which one is chosen at random? The probability of each is given by the square of the size of that outcome's contribution to the wave function, a rule Max Born wrote down, also in 1926, in a footnote added while his paper was already in proof. That footnote is one of the most consequential sentences in the history of science. It earned him the Nobel Prize in 1954, 28 years later. Now compare the two rules, property for property, and watch what happens. The Schrödinger equation is smooth. Collapse is a discontinuous jump. The Schrödinger equation is deterministic. Collapse is irreducibly random. The Schrödinger equation is reversible and preserves every scrap of information. Collapse is irreversible and destroys all the possibilities that did not happen. You cannot run it backwards. Once the answer is 1, the memory that it was ever many is simply gone. And the Schrödinger equation creates superposition as a matter of mathematical necessity. Collapse destroys it. These two rules are not merely different. They are not two chapters of a single story. In every structural respect that a physicist would care about, they are opposites, sitting on facing pages, both required, both used every single day by everyone. John von Neumann, one of the great mathematicians of the 20th century, made all of this official in 1932 in a book called The Mathematical Foundations of Quantum Mechanics. He called them Process 2 and process 1. Process 2 being the smooth evolution, process 1 being the jump. Giving them numbers made the situation precise. It did not make it better. What von Neumann had done, in effect, was to write the discontinuity into the Constitution. It is worth knowing that Schrödinger himself never accepted the second rule. He fought it for decades. When he invented that cat, the one in the box, the one that has been on 1,000 t-shirts since, he was not offering physics a charming mascot for quantum weirdness. He was trying to demonstrate that the second rule leads somewhere absurd, and that a theory which produces absurdity has something wrong with it. The cat was an argument. It got adopted as a logo, and there is a modern industry sitting directly on top of this seam, which most people never notice. A quantum computer is a machine that does all of its actual work inside Rule 1, inside the superposition that linearity permits, and then invokes Rule 2 at the very end to read out an answer. Every dilution refrigerator, every error correction scheme, every $1 billion of investment in the field is, in engineering terms, an effort to stay in Rule 1 for as long as possible, and then step deliberately into Rule 2 at a moment of your choosing. The whole enterprise runs across the join between two rules that nobody can reconcile, and now we arrive at the crack. The theory does not tell you when to switch. There is no equation in quantum mechanics, none, anywhere in any formulation, that specifies the conditions under which the smooth evolution stops and the jump happens. There is no threshold, there is no trigger, there is no term in the Schrödinger equation that grows large under certain circumstances and takes over. The switch between Rule 1 and Rule 2 is thrown by hand, by the physicist, at whatever point in the calculation the physicist has decided that a measurement has occurred. That is not a subtlety of interpretation. That is not a philosophical quibble about what the equations mean. It is a missing piece of the machinery, a step in the procedure that the theory outsources to the judgment of the person doing the arithmetic, and it has been missing since the two rules were written down, within months of each other, by two men who were both, at the time, quite pleased with themselves. I want to make sure the strangeness of this lands, so let me put the two facts next to each other. Fact 1. Quantum mechanics contains a rule with no equation, applied at a moment the theory cannot specify, by a human being using their own judgment. Fact 2. That same theory, using that same two-step procedure, predicts the magnetic moment of the electron to about 12 decimal places. 12. If you measured the distance from here to the moon that accurately, you would be arguing about the width of a human hair. It is the most precisely confirmed prediction in the entire history of science, and it comes out of a framework whose second rule is essentially a note in the margin saying, and then something happens. Accuracy and coherence have come completely apart. The theory works flawlessly and cannot say what it is doing, and I find that genuinely hard to get comfortable with, because in every other part of physics those two things travel together. When a theory predicts to 12 decimal places, we usually take that as evidence we have understood something. Now, the obvious reply is waiting, and you have probably already thought of it, because everybody thinks of it, and it is a perfectly reasonable thing to think. The reply is, fine, but we know when to switch. You switch when you make a measurement. That is not mysterious. That is just what an experiment is. It is a good reply. It is the reply the founders of the subject gave, and it survives right up until the moment somebody asks the next question, which is the question that has been quietly demolishing this answer for 90 years. What exactly is a measurement? Part 3. The word nobody can define. Let us try to answer it honestly. What is a measurement? The first instinct is to say that a measurement is an interaction. Something touches the electron, and the touching forces it to commit. That sounds right for about 4 seconds, until you remember that the universe is nothing but interactions. Every particle in existence is constantly being bumped, pulled, scattered, and jostled by every other particle within reach. Air molecules collide billions of times a second. Photons stream through everything. If every interaction were a measurement, then nothing would ever be in superposition for longer than an instant anywhere, and the entire quantum world would have collapsed before it started. Interference patterns would not exist. They do exist. So interaction alone is not it. The second instinct is size. Measurements involve big things, detectors, screens, laboratories. Small things stay quantum, big things go classical, and the switch happens somewhere in between. This has the great virtue of matching everyday experience, and the fatal flaw of containing no number. How big? 10,000 atoms? A million? A gram? Nobody has ever been able to write down the threshold, and, as we will see shortly, every time someone has gone looking for it experimentally, it has failed to be where they expected. The third instinct is that a measurement produces a record, something permanent, something written down. But a record is just more particles in a particular arrangement. Ink on paper is molecules. A magnetic bit on a hard drive is electron spins. A memory in your head is a pattern of ions and proteins. All of those obey the Schrödinger equation like everything else, and none of them contains a clause that says, and at this point, stop obeying it. You can keep going. Irreversibility, amplification, thermodynamic entropy, the involvement of many degrees of freedom. Every proposal either fails to pick out a specific moment, or, when you look closely, quietly smuggles in a human being at the end of the chain. Von Neumann made this failure precise, and the argument he gave is so clean that it has never really been improved on. It is now called the von Neumann chain. Start with the electron. It is in a superposition of two possibilities. It arrives at a detector, and the detector responds. One way if the electron is in the first state, another way if it is in the second. But the detector is made of atoms, and atoms obey rule 1, so what actually happens is that the detector becomes entangled with the electron. Now the superposition is bigger. It is not electron here plus electron there. It is electron here and detector reading A, plus electron there and detector reading B. Keep going. The detector drives a pointer. The pointer joins the superposition. Photons bounce off the pointer and carry the information into the room. They join too. Some of those photons enter the physicist's eye and strike her retina. The retina joins the superposition. Her optic nerve fires and joins. Her visual cortex processes the signal and joins. Every single one of these steps is a perfectly ordinary physical interaction, described perfectly well by Rule 1, and every single one of them makes the superposition larger rather than resolving it. At no point in that chain does the mathematics offer a place to cut. That is the phrase people use for it, the cut, or the Heisenberg cut. You draw a line somewhere in the chain and declare that everything on the quantum side of the line gets Rule 1, and everything on the classical side gets Rule 2. And here is the thing von Neumann proved, which sounds like reassurance and is actually the alarm. You can put the line anywhere you like, and you get exactly the same experimental predictions. Cut at the detector, cut at the pointer, cut at the retina. Same answers, every time. People often teach that as a feature. Look how robust the theory is. It does not matter where you draw the line. I would ask you to hear it the other way. If a theory gives identical answers no matter where you place its single most important dividing line, that is the theory telling you the line is not in the theory. It is not a physical boundary. It is a decision made by the person doing the calculation, for convenience, and the universe never sees it. Careful writers in this field separate the difficulty into two problems, and the distinction is going to matter enormously later, so let me give it to you now while it is cheap. The first is the problem of outcomes. Why does anything definite happen at all, rather than everything continuing to happen at once? The second is the problem of the preferred basis. Given that something definite happens, why is it always definite in terms of position? Why do we find the cup here or there, rather than in some exotic blend of here and there that the mathematics would allow just as easily? Two problems. Remember that there are two, because one of them is about to be solved beautifully, and the other one is not. The Copenhagen interpretation, associated above all with Niels Bohr and Werner Heisenberg, handled this in a way that was far more thoughtful than its caricature. Bohr's position was that the apparatus must be described in classical terms, not because atoms stop being atoms when you assemble them into a machine, but because doing science at all requires being able to say, unambiguously, the pointer landed here. Communication about experiments needs a language of definite facts, so the classical description is not an oversight in the theory. It is a precondition for having a theory at all. That is a serious argument, and I do not want to be glib about it. But you can see the price. What Bohr is describing is a theory of the universe that requires part of the universe, the part with the instruments and the physicists in it, to stand outside the theory and be described by different rules, and you are made of the same particles as the detector. So either you are somehow standing outside physics, which is not a position anyone wants to defend for long, or the theory is incomplete. John Bell, the same Bell whose theorem about entanglement reshaped the whole subject, lost patience with this in a short, blazing paper in 1990 called Against Measurement. In it, he listed words that he argued should be banned from any formulation of quantum mechanics claiming to be fundamental. The list is worth hearing in full: system, apparatus, environment, microscopic, macroscopic, reversible, irreversible, observable, information, measurement. Every one of them, he pointed out, is vague at precisely the place where precision is required, and he had a phrase for the standard defense, that the theory works fine for all practical purposes. He shortened it to FAPP, and he used it as an accusation. Fine for all practical purposes is an excellent standard for an engineer. It is not an acceptable standard for a description of what the world is. There is one more entry in this history that I want to plant now and come back to much later, because it explains something about how this whole field is regarded. In the 1960s, Eugene Wigner, a Nobel laureate, one of the most technically formidable physicists of his generation, followed the von Neumann chain all the way to its end and concluded, seriously and in print, that the thing that stops it must be consciousness. Not because he was a mystic, because he went looking for anything in the physics that could terminate the chain, and he could not find one, and the only thing at the end of the chain that seemed categorically different from everything before, it was the fact that somebody now knew. He later abandoned the position. We will get to why and to what it cost this subject that a man of his stature ever held it. But hold on to the shape of what we have just done, because this is the crack, fully exposed. Quantum mechanics predicts the magnetic moment of the electron to 12 decimal places. It underpins every semiconductor, every laser, every magnetic resonance scanner, every nuclear reactor on the planet. It is the most thoroughly confirmed description of nature our species has ever produced, and it cannot tell you what an event is. It cannot say what happened when something happened. It has total precision about the statistics of outcomes and total silence about the occurrence of outcomes, about the plain fact that things actually take place, one at a time, in a definite order, in a world where the cup is on the table and not also on the floor. That is the flaw. That is the whole flaw. It is not hidden in some exotic corner of the theory. It is on page 1 in the definition of what the theory is for. For most of the 20th century, there was one last line of defense, and it was a good one. Quantum mechanics is a theory of small things, the argument went. Classical mechanics is a theory of big things. The crack is real, but it is sealed off, down there at the scale of atoms, where nothing you care about lives. That defense has been dismantled, not by philosophers, by people building machines. Part 4. The cat was never the point. Before we go up the ladder, I want to rescue an animal. Everybody knows Schrödinger's cat. A cat in a box, a vial of poison, a radioactive atom that may or may not have decayed, and therefore a cat that is somehow both alive and dead until you open the lid. It has been on coffee mugs and T-shirts and the side of laboratory vans for 50 years, and it is almost universally presented as a delightful illustration of how strange the quantum world is. That is not what it was. Schrödinger published it in 1935, and he was not being delightful. He was furious. He had spent years objecting to the second rule, and the cat was his attempt to make the objection impossible to wave away. The argument runs like this. Quantum mechanics says the atom is in a superposition of decayed and not decayed. Fine, you say, atoms are strange. But the apparatus links the atom to the vial and the vial to the cat, and Rule 1 applies to all of it. So if you take the theory seriously and do not throw the switch by hand, the theory says the cat is in a superposition too. And that, Schrödinger was pointing out, is ridiculous. Cats are not in superpositions, so something in your theory is wrong. He was making a reductio, an argument that a premise must be false because it leads somewhere absurd. And over the following decades, the physics community performed one of the most elegant conjuring tricks in intellectual history. It took the absurd conclusion, put it on a mug, and called it a wonder. The objection was domesticated into a mascot. Schrödinger died in 1961, still unhappy. The reason I want that on the record before we continue is that the whole defensive line I mentioned a moment ago, quantum for small, classical for large, was always a promissory note. It was never a discovery. Nobody ever found the boundary. They assumed there was one, because there obviously had to be one, because you have never seen a cat in two places. So let us go and look for it. The first rung was electrons in the 1920s, and that surprised nobody for long. Electrons are the archetypal quantum object. Of course they interfere. The second rung took 70 years, and it is the one that changed the mood. In 1999, a team in Vienna, including Marcus Arndt and Anton Zeilinger, published in Nature the interference of carbon-60, buckyballs, 60 carbon atoms bonded into a hollow sphere about a nanometer across, with a mass of 720 atomic mass units. And I want you to hold what that object actually is, because molecule flattens it. A buckyball is a cage. It has a shape you could build out of plastic and put on a shelf. It has an internal temperature. Its atoms are vibrating against each other in dozens of different modes. In the Vienna experiment, the molecules were hot enough to be radiating thermal photons as they flew. They were glowing, faintly in the infrared, the entire way through the apparatus. And they interfered. A hot, complicated, structured object, throwing off light as it went, still went through both slits and added up with itself on the far side. The third rung came in 2019, from largely the same group. Yakov Fein, Marcus Arndt and colleagues published in Nature Physics the interference of custom-built molecules called functionalized oligoporphyrins with masses exceeding 25,000 daltons, that is about 2,000 atoms in a single molecule. A significant part of the achievement was not physics at all, but chemistry. The molecules had to be synthesized specifically to be heavy, to survive being made into a beam, and to not stick to every surface they touched. The interferometer they flew through was 2 meters long. Imagine standing at that machine while it runs. A single molecule leaves the source, 2,000 atoms. Not a point, not an abstraction, not a convenient idealization in an equation. A small, warm, elaborate thing with a definite architecture, a thing that a chemist designed and built and could draw for you. It travels, it reaches the grating, and it does not choose. It goes every available way at once, and 2 meters later it lands somewhere on the far side, one single dot, in one single place, and then another one, and another, for hours, and slowly, out of thousands of individual arrivals that each looked like a particle landing in a spot, a pattern assembles itself on the detector, bands of many and bands of almost none, and the pattern is the signature of a wave that took all the paths simultaneously. Every one of those molecules was, on its way through, in a superposition of routes separated by a distance you could see under a microscope. There is no line in that apparatus. There is no point at which the machine says, "This one is too big." Every molecule they could get through the instrument behaved exactly the way an electron behaves. The fourth rung landed this year. In 2026, the Vienna group reported in Nature the interference of sodium metal clusters exceeding 175,000 daltons, another factor of 7 up from the 2019 record, using a new instrument built for the purpose. There is a formal number the field uses to score these experiments called macroscopicity, which captures how badly a given result would constrain any hypothetical mechanism that kills superposition. The 2026 result comes in at 15.4, the highest yet achieved. And then there is the other frontier, which is stranger still, because it involves something that is not a molecule at all. In April of 2023, a team led by Yuan Chu at the Swiss Federal Institute of Technology in Zurich published in Science the creation of a Schrödinger cat state in a bulk acoustic wave resonator, essentially a small sapphire crystal, ringing. They put it into a superposition of 2 opposite phases of the same oscillation. The effective mass involved was about 16 micrograms, and the object contained something on the order of 10 to the 17th atoms. I want to be honest about what that experiment is and is not, because it gets overstated. The 2 superposed states are not 16 micrograms of sapphire sitting in 2 different places on the bench. They are 2 opposite phases of a vibration, and the actual spatial separation involved is tiny. That distinction will matter later. But the mass is the mass, and 16 micrograms is not an atomic quantity. It is a mote of dust. It is a thing you could weigh on a good laboratory balance, sitting in a superposition in a fridge in Switzerland. Remember that number, 16 micrograms. I am not going to tell you yet why it matters, but when we come back to it in about an hour, it is going to stop being a curiosity and become one of the most suggestive coincidences in modern physics. There is a third line of attack running in parallel, and it is worth a moment because it is where the next decade of this story will probably be written. Instead of firing molecules through a grating, you take a single solid particle, hold it in midair with a laser light so that it touches nothing at all, and then cool its motion down until it is as still as the laws of physics permit. In 2020, Uroš Delić, Marcus Aspelmeier, and colleagues in Vienna published in Science the cooling of a levitated silica sphere about 150 nanometers across into its motional quantum ground state, starting from room temperature. Ground state means the particle is no longer jiggling for any thermal reason. The only motion left is the irreducible quantum minimum. That is the prerequisite for the real prize, which is putting an object like that into a superposition of two positions and watching what happens. Nobody has done it yet. Several groups are trying. What all three approaches have in common is that none of them is an accident. Nobody's going to stumble into the answer here. Every rung on this ladder took roughly a decade, a purpose-built machine, and a small career's worth of somebody's patience. And every one of them was a deliberate assault on the same question. Is there a size at which the universe stops allowing maybes? So the ladder has been climbed for a century, one purpose-built machine at a time, roughly a decade per rung, and at no point has anyone found the top of it. The boundary between the quantum world and the classical one has been pushed from a single electron up to objects with 2,000 atoms, then 175,000 Daltons, then to a crystal you could weigh, and it has not broken. It has just moved. Which raises an obvious question. If the promissory note was never paid, if nobody ever found the line, then why is the physics community not in a state of permanent crisis about this? And the answer is that they have something much better than a line. They have an explanation. It is real, it is measured, it is quantitative, and it is genuinely one of the best pieces of physics of the last half-century. It just does not do quite what most people think it does. Part 5. The answer. Everyone gives. I want to do something now that I think is only fair, which is to give the other side of this argument its very best shot before I say a word against it. Because there is a temptation, in a video with a title like this one, to imply that physicists are being lazy or evasive, that there is an obvious hole and everyone is politely pretending not to see it. That is not what is happening. The overwhelming majority of physicists have an answer to why you never see a cat in two places, and their answer is not a shrug. It is one of the genuinely great achievements of 20th century theoretical physics. It makes numerical predictions. Those predictions have been measured, and they were right. It is called decoherence, and it starts with a man working alone. Hans-Dieter Zeh was a physicist at Heidelberg who, in 1970, published a paper in the journal Foundations of Physics on the interpretation of measurement in quantum theory. It was, in retrospect, the beginning of the whole field. At the time, it was close to career suicide. The measurement problem in 1970 was regarded as a question that serious people had stopped asking. It had been settled, in the sense that everyone had agreed to stop arguing about it, which is not the same thing. Zeh's paper was rejected, then ignored, and he later described the reception as damaging to his standing in the field. It took roughly 20 years for the idea to be recognized as important. Here is the idea. Nothing is ever isolated. That sounds too simple to carry any weight, so let me make it concrete. Take a dust grain, put it in a sealed box, pump out all the air so it is a hard vacuum, cool the walls of the box down toward absolute zero, wrap the whole thing in lead. Have you now isolated your dust grain? You have not. Passing through that box, through the lead, through the vacuum and through the grain, are the photons of the cosmic microwave background. The leftover light of the Big Bang itself, cooled over 13.8 billion years to a faint microwave glow that fills the entire universe at a density of about 411 photons per cubic centimetre. They are everywhere. There is no shielding against them that does not itself radiate. Every cubic centimetre of space you have ever occupied has 400 photons of the early universe in it right now, and every one of those photons that bounces off your dust grain carries away information. That is the whole mechanism. If the grain is in a superposition of two positions and a photon scatters off it, then the photon that flies away is slightly different depending on which position the grain was in, which means the photon and the grain are now entangled, and the moment that happens, the interference between the grain's two possibilities is no longer something you can find by looking at the grain. It has not been destroyed, it has been relocated into a correlation between the grain and a photon that is now halfway across the room and heading for the wall. To see the interference, you would have to catch that photon and bring it back and recombine it perfectly, and then the next one, and the next. And there are, depending on the environment, somewhere between millions and unimaginable numbers of them per second. The numbers are what turn this from a nice story into overwhelming physics. In 1985, Erich Jüss and Dieter Zeh worked out the timescales, and they are difficult to hold in your head. A dust grain 10 micrometers across, that is 1/10 the width of a human hair, a thing you could just about see, sitting in ordinary room air, loses its coherence in about 10 to the minus 31 seconds. That number does not mean anything to a human nervous system, so let me translate it. Light, moving at 300,000 kilometers a second, would in that time cross about 1/millionth of the width of a single proton. The superposition is gone before anything in the universe could conceivably have travelled far enough to notice it existed. Take away the air, perfect vacuum, refrigerated, shielded from everything except the cosmic microwave background, which you cannot remove. The same grain now decays in about 10 to the minus 7 seconds, a 10 millionth of a second. You have improved the situation by 24 orders of magnitude, and it is still hopeless. That is why you have never seen a cat in two places. Not because the universe forbids it, because you are large and warm and surrounded by light, and the evidence is stolen from you faster than any instrument, or any eye, or any nervous system could conceivably record it. There is one more feature of these numbers worth pausing on, because it explains something we saw in the last part. Decoherence times do not scale gently with size. Make an object modestly bigger, and its coherence time can drop by many orders of magnitude, because there is more surface for the environment to touch, and more mass for each touch to register against. That is exactly why every rung of the interference ladder cost a decade and a purpose-built machine. The Vienna group is not fighting a difficult engineering problem, they are fighting an exponential. Every extra 1,000 atoms they push through an interferometer has to be bought with colder beams, longer flight paths, better vacuum, and cleverer chemistry, and the price goes up faster than the achievement does. Wojciech then took the idea a decisive step further, and this is the part that answers the second of our two problems from earlier, the preferred basis. Why is the classical world made of objects in definite places, rather than objects in definite momenta, or definite blends of position and momentum? Zurich's answer, which he called einselection, short for environment-induced superselection, is that the environment does not interact with objects in a neutral way. Photons and air molecules interact with things according to where they are. So position is the property that gets copied, over and over, into the environment. And whatever property the environment copies is the property that survives because it is the one everybody can agree on. The classical world is made of things in places because where is what the universe keeps writing down. He later extended this into an idea called quantum Darwinism, which explains something even more basic, why we all agree. The environment does not make one copy of a system's position. It makes an enormous number of redundant copies, scattered into countless independent fragments. You and I can each intercept a different fragment, read the same answer, and neither of us disturbs the original. Objectivity in this picture is a form of broadcasting, and none of this is theoretical arm-waving. It has been watched. Serge Haroche and his group in Paris spent years building cavity quantum electrodynamics experiments in which a superposition of microwave field states could be created inside a superconducting cavity, and then observed, gently, over time, as it lost its coherence, watching a small cat state die in real time, photon by leaking photon, on a schedule that matched the theory. Haroche shared the Nobel Prize in Physics in 2012 for that work. Decoherence is not a philosophical proposal. It is a measured process with a measured rate, and modern quantum computing is essentially a war against it. Every dilution refrigerator at 10,000ths of a degree above absolute zero, every layer of magnetic shielding, every error correction scheme exists to hold the environment off for a few microseconds longer. It is also worth noticing what decoherence does not require, because this is the source of its enormous authority. It does not add a single new term to the Schrödinger equation. It does not postulate a new force, a new particle, a new constant, or a new rule. It is nothing but Rule 1, applied honestly to the fact that systems are never alone. Everything I have just described falls out of taking the existing theory completely seriously and refusing to pretend that anything is ever isolated. For a physicist, that is the most attractive kind of explanation there is. No new machinery, no free parameters, and it makes numbers you can go and check. Zurich's article in Physics Today in 1991 is probably the piece that carried the idea out of specialist circles and into the general physics culture, and after that it moved fast. Within about 15 years, decoherence went from an obscure heresy that had cost Zay professional standing to the standard thing you say, when an undergraduate asks why the cat is not in two places. That is an unusually rapid rehabilitation, and it happened because the explanation is genuinely excellent. We have spent time on this channel before on exactly why you cannot see the quantum world, so I will not walk the whole road again. The summary is that decoherence is true, it is quantitative, it explains why the classical world looks the way it does, it explains why objects have positions, and it explains why we all agree about them. So the case is closed, isn't it? That is certainly the working assumption of most of the field, and I want to be clear that it is not an unreasonable one. But Roger Penrose, a man who has been right about several things nobody expected him to be right about, looks at this same explanation and uses a very specific word for it. He calls it cheating. Part 6. The glitch of logic. This next stretch is the hinge of the entire video, and it is subtle, so I'm going to take it slowly and I'm going to say it more than once in more than one way. If you are drifting off, this is a good place to let the words wash over you, because I will come back and restate the conclusion plainly at the end. When a system becomes entangled with its environment, a physicist has a bookkeeping problem. The full quantum state now includes the system and every photon and air molecule it has touched, which is an object of unimaginable complexity that nobody can write down and nobody wants to. So they do something perfectly sensible. They mathematically discard the parts they are not tracking, the photons that flew off, the air molecules that bounced away, and keep only what is left. The operation is called taking the partial trace, and the thing it leaves behind is called a reduced density matrix. And here is the beautiful result. After decoherence has run its course, that reduced density matrix is diagonal, which means, if you look at it, it reads like an ordinary list of classical probabilities. 60% chance it is over here, 40% chance it is over there. There are no interference terms left. There is no trace of quantum weirdness in it at all. It looks exactly like a coin that has already landed sitting under someone's hand, waiting to be revealed. And that is the trap, because it is not that, and the distinction has a name, and it was made sharp by the French physicist Bernard d'Espagnat in 1976, and it is the difference between what he called a proper mixture and an improper mixture. A proper mixture is genuine ignorance. Somebody flipped a coin. It landed. It is heads or it is tails, definitely one, and I simply have not looked. The probabilities in my description are about my state of knowledge. The fact of the matter already exists. An improper mixture is what you get when you take a partial trace of an entangled whole, and in that case the global state, the system plus everything it is entangled with, is still a single, pure, perfectly coherent quantum state. It is still in superposition. It is still evolving smoothly under Rule 1. Nothing anywhere in the universe has become definite. The two branches are both fully present, both fully real as far as the mathematics is concerned. What has happened is only that the evidence of their coexistence has been spread so thinly across so many far-flung photons that no local measurement will ever reassemble it. Those two situations, the coin that landed and the coin still spinning in a way you can no longer see, are described by exactly the same matrix, and they mean completely different things. Let me try an analogy, and then I will immediately tell you where it breaks, because analogies in this area are dangerous. Imagine two sealed envelopes. In the first, someone wrote either the word yes or the word no, sealed it, and handed it to you. There is a fact inside that envelope. You do not know it. That is a proper mixture. Real ignorance about something already settled. In the second envelope there is a sheet of paper that has not been written on yet, and it is connected by a mechanism you cannot see and cannot break to a second sheet in a second envelope that somebody carried off to the other side of the world an hour ago. Nothing has been written on either sheet. Nothing has been decided, but every calculation you can perform on your envelope alone, without ever getting hold of the other one, gives you exactly the same answers as the first case. 50% yes, 50% no. Your envelope, considered by itself, is indistinguishable from an envelope containing a fact. Where the analogy breaks is that the second envelope is not connected to one other sheet. It is connected to something on the order of a billion other sheets, scattered outward at the speed of light in every direction, and the connection cannot be cut, only diluted. That is what an improper mixture actually is, and the reason it matters is that the first envelope contains an answer, and the second one does not, and no amount of looking at your own envelope will ever tell you which kind you are holding. So when a physicist looks at that diagonal matrix and says, right, so it is either here or there, with these probabilities, that step, that small and utterly natural step, is not something the mathematics did. It is something the physicists did. It is an additional assumption inserted silently in the space between one line of algebra and the next. And I want to name what that assumption is, because it is not a new one. It is the collapse postulate. It is Rule 2. It is the second rule, wearing a different hat and coming in through a side door. That is what Penrose means. His own words, in an interview, are that the standard procedures slightly cheat, or really fundamentally cheat, I should say. He describes the density matrix being introduced as a better description of the world because it includes all the random things, and then being read as a probability mixture of different states. And he says, in there is a little glitch of logic, which people like to sweep under the carpet. And what has actually happened, he says, is that you have collapsed the wave function without saying it out loud. The physicist Stephen Adler put the same objection in the title of a paper in 2003, Why Decoherence Has Not Solved the Measurement Problem. He was responding to another physicist who had claimed it had. Let me now state the conclusion as cleanly as I can, because this is the sentence the rest of the video hangs on. Decoherence explains, completely and quantitatively and beyond any reasonable dispute, why you cannot see the alternatives. It does not explain why only one of them happens. Those are different questions. Remember the two problems I flagged earlier, the problem of the preferred basis and the problem of outcomes. Decoherence solves the first one magnificently. In-selection tells you exactly why the world is carved up into positions rather than something else, and quantum Darwinism tells you why everybody agrees. It is a triumph. And it does not lay a finger on the second one. The branches do not disappear. They become undetectable. Every alternative outcome is still there in the global wave function, evolving away, and the question of why you are experiencing precisely one of them is exactly as open as it was in 1926. There is something almost perverse in how this played out historically. Decoherence did not make the measurement problem easier to solve. It made it harder to see. Before 1970, the problem was embarrassing and visible. There was a naked hole in the theory and everyone could point at it. After decoherence became standard, there was a sophisticated, quantitative, experimentally confirmed account of the whole phenomenon that covered the whole with something that looks, from every practical angle, exactly like a flaw. You can stand on it. You can build on it. You can run an entire career across it and never fall through. The hole is still there. It is just no longer where anybody's looking. Now, I have to be fair here, and there are two serious replies. The first is the Everettian, or many worlds, reply, and it is not a dodge. It is arguably the most logically economical position available. It says, you're right, the branches do not go away. They are all real. Each branch contains a version of the observer who sees one definite outcome and is entirely convinced it was the only one. On this view, there is no extra rule needed and no problem to solve because nothing was ever discarded. That is coherent, it is elegant, and the price is that every outcome that did not happen to you happened. The second reply is more pragmatic, and it says the whole proper versus improper distinction is a philosopher's ornament, that probabilities in physics were never really claims about pre-existing facts, and that a theory which predicts every observation correctly has discharged its duty in full. That is also a serious position, and it is roughly where a lot of thoughtful working physicists actually live. But notice what neither reply says. Neither of them says the objection is confused. Almost nobody who works on the foundations of quantum mechanics claims that the improper mixture is straightforwardly a proper one. The argument is not about whether the gap is there. The argument is about whether the gap matters, whether it is a crisis or a footnote or a question about words, and there is a simple test I would offer you for deciding that for yourself. If decoherence had actually solved the measurement problem, then there would be nothing left for the interpretations to argue about. The debate would have ended in 1990. Instead, half a dozen serious, mutually incompatible interpretations of quantum mechanics remain alive and defended by intelligent people, each of them charging a different and substantial price. The persistence of that argument decades after the supposed solution is itself the evidence that a hole remains. So that is where we stand. And before we go looking for what might actually fill it, I want to stop and gather the pieces, because we have covered a lot of ground and the next part of tonight goes somewhere quite different. Part 7. Let's put the pieces together. Let us step back for a moment. We have been building something carefully, piece by piece, and it is worth stopping here at roughly the halfway mark and stacking the pieces up where you can see all of them at once. because the second half of tonight goes somewhere very different from the first, and I want you to be standing on solid ground when it does. Here is where we are. The first piece is that quantum mechanics contains two rules for how the world changes, and they are opposites in every respect that matters. One smooth, deterministic, reversible and generous with possibilities, the other abrupt, random, irreversible and ruthless with them, and there is no law anywhere in the theory that says when to stop using the first and start using the second. That decision is made by a human being, by hand, at whatever moment seems appropriate. It has been that way since 1926. The second piece is that the natural defense, that the switch happens when you make a measurement, dissolves the moment you ask what a measurement is. Every candidate definition either fails to single out a moment or smuggles in a person. Von Neumann's chain runs from the electron all the way into the physicist's brain, with Rule 1 applying perfectly at every link, and the cut can be placed anywhere along it with identical results, which tells you the cut is not in the physics. And the last line of defense, that this only bites at atomic scales, safely away from anything you care about, has been dismantled by experiment. The boundary has been pushed from an electron to a molecule of 2,000 atoms to a sapphire crystal weighing 16 micrograms, and it has never once been found. The third piece is that the standard answer, decoherence, is genuinely excellent and does not close the hole. It explains, beautifully and with real numbers, why you cannot see the alternatives. A dust grain in air loses its coherence in 10 to the minus 31 seconds, and even in perfect vacuum under nothing but the light of the early universe, in 10 to the minus 7. It explains why the world is made of things in places rather than things in stranger states. It explains why everyone agrees. And then, at the very last step, when the diagonal matrix is read as a list of things that might have happened, rather than things that are all still happening, the second rule is quietly slipped back into the argument without announcement. Penrose calls it a glitch of logic. Nobody serious claims he has misunderstood the mathematics. They claim it does not matter very much. So, a hole, a failed patch, and a superb explanation that turns out to be an explanation of something adjacent. Now here is the question that takes us into the rest of the night. If the hole is real, if there genuinely is something missing from quantum mechanics, then what could possibly fill it? And notice that most of the available answers do not fill it at all. They reframe it. Many World says the missing piece is missing because you were wrong to want it. Everything happens and nothing collapses. The pilot wave picture says particles always had definite positions, and the whole puzzle was an artifact of leaving them out. Various relational and observer-centered views say that facts were never absolute to begin with. Every one of those is a serious position, and every one of them makes exactly the same predictions as the textbook theory, down to the last decimal place. They are different stories told over identical data. You cannot do an experiment to choose between them, which means choosing between them is a matter of taste, and physicists are trained, correctly in my view, to be suspicious of matters of taste. But there is one other kind of answer, and it is categorically different. Suppose the missing piece is not a story at all. Suppose it is physics, an actual, additional, physical process that is genuinely happening out there in the world, which was left out of the equations because nobody noticed it. Suppose the wave function really does collapse, all by itself with no observer anywhere in the picture, because something in nature makes it collapse. That would be a different equation, and a different equation makes different predictions, and different predictions can be checked and can be wrong. There is exactly one candidate of that kind that has serious support from a serious physicist, and the physicist in question is one of the most decorated living scientists in the world, and his proposal is regarded by a substantial fraction of his own field as facing entirely the wrong direction. And I should say plainly what kind of claim that is, because it is unusual. It is not an interpretation. It is a proposal that the Schrödinger equation, the most successful equation ever written, is not exactly correct. That it is an extraordinarily good approximation to something slightly different, in the same way Newton's law of gravity turned out to be an extraordinarily good approximation to something slightly different. That is a large thing to say, and the person saying it knows exactly how large it is. Everyone else is trying to make gravity quantum. He wants to make quantum mechanics gravitational. Part 8. The Man Who Went the Other Way. Roger Penrose was born on the 8th of August 1931 in Colchester, in the east of England, into a household that made things. His father, Lionel, was a medical geneticist with an obsessive interest in puzzles and patterns and mechanical toys. His mother was a doctor. The children drew constantly, and in the 1950s Penrose and his father together devised two objects that you have absolutely seen, whether or not you know their names: the impossible triangle, 3 bars that meet at right angles in a way that no solid object can, and the endless staircase that climbs forever and returns to where it started. They published them. A Dutch artist named Moritz Cornelis Escher saw them, wrote to the Penroses, and turned them into two of the most famous images of the 20th century: the waterfall that feeds itself and the monks marching perpetually upward around a rooftop. That is a useful thing to know about him, because Penrose is not primarily a symbolic thinker. He has said, repeatedly, that he thinks in pictures, that he works out arguments by drawing them, and that the algebra comes afterwards as a way of communicating what he has already seen. It is going to matter later, because the argument at the centre of tonight is fundamentally a picture, and it can be held in your head as a picture without any mathematics at all. In the 1970s he found something else. He was playing with the problem of tiling a plane, covering a flat surface with shapes, with no gaps and no overlaps, and he found sets of tiles that cover the plane in a pattern that never exactly repeats, with a 5-fold symmetry that everyone had believed was impossible for a tiling. They are called Penrose tilings. They were regarded for about a decade as a very pretty piece of recreational mathematics with no application to anything. Then, in 1982, a materials scientist named Dan Shechtman found a metal alloy whose atoms were arranged in exactly that kind of non-repeating 5-fold pattern. Quasi-crystals. Nature had been building Penrose tilings all along. Shechtman was told by colleagues that there was no such thing and that he should go and read a textbook. He won the Nobel Prize in Chemistry for it in 2011. That is the pattern of the man's career. He finds things before anyone knows they are things. The work he is best known for came in the 1960s, and it concerned black holes at a time when serious physicists were not sure black holes were real. The equations of general relativity had solutions containing singularities, points where the curvature of space-time becomes infinite and the theory stops making sense. But the general view was that these were artifacts of oversimplification. Real stars are lumpy and spinning and imperfect, and the assumption was that if you collapsed a realistic star, the imperfections would prevent everything from converging on a single point. Penrose proved otherwise. Using topological methods that were entirely new to the field, he showed that once a collapsing region passes a certain threshold, a singularity becomes unavoidable, regardless of symmetry, regardless of lumpiness, regardless of anything. The theory predicts its own breakdown, robustly. He and Stephen Hawking then extended the result to the universe as a whole, which is why the Big Bang is understood as a singularity too. It took 55 years for that work to be recognized with the highest honor in the field. In 2020, Roger Penrose received half of the Nobel Prize in Physics, with the citation for the discovery that black hole formation is a robust prediction of the general theory of relativity. The other half was shared by Reinhard Genzel and Andrea Ghez for their decades of patient observation of the stars whipping around the supermassive object at the center of our own galaxy. And here is my favorite thing about him. If you ask Roger Penrose what he is proudest of, he does not say the singularity theorems. He says twistor theory. It is an idea he traces back to around 1963 and first published as a paper called Twistor Algebra in the Journal of Mathematical Physics in 1967. The proposal is difficult to explain quickly, and Penrose himself tends to say it is a bit too technical to go into, but the flavour of it is this. Instead of building space-time out of points, build it out of light rays. Take the paths of light as the primary objects, and points become secondary things, the places where light rays happen to meet. Then rebuild the geometry on a complex number foundation. The whole construction was designed, from the very start, to treat relativity and quantum theory as things that ought to speak the same language, rather than as two systems to be bolted together. More than 60 years later, twistor ideas have spread into pure mathematics and into the machinery particle physicists use to calculate what happens when particles collide, in forms he says he did not anticipate, and not always in the version he originally proposed. There are workshops on it. There are young people who have built careers on it who were not born when he wrote it down. He held the Rouse Ball Professorship of Mathematics at Oxford from 1973 until 1998, and has remained there, emeritus, ever since. As of this summer, he is 94 years old and he is still publishing, still arguing, and still, by the standards of his own field, comprehensively out of step. Because that is the other thing you need to know about him. Penrose holds several positions that most of physics considers eccentric, and he holds them in public without apology for decades at a time. He has proposed a cosmology called conformal cyclic cosmology, in which our entire universe is one aeon in an endless sequence, and the remote cold future of one aeon becomes the hot dense beginning of the next. Most cosmologists do not accept it. In 1989 he published a book called The Emperor's New Mind, arguing that human mathematical understanding is non-computable, that no algorithm, no matter how sophisticated, can do what a mathematician does when she simply sees that something is true. Most computer scientists do not accept that either. We are going to come back to that book at the very end of tonight, because it turns out to have cost the idea at the centre of this video more than anything else in the story. The point is not that he is always right. He is not. The point is that he has an unusually high tolerance for being the only person in the room holding a position, and an unusually good track record of eventually being joined there. Now, all of that is context. Here is why it matters tonight. For the past 50 years, the central project of theoretical physics has been to quantize gravity. The reasoning behind that goal is so widely shared that it is rarely stated out loud, so let me state it. Quantum mechanics is a theory of small things: particles, atoms, fields. General relativity is a theory of big things: stars, galaxies, the shape of the universe. Big things are made of small things. Therefore, the theory of small things must be the more fundamental one, and the job is to take the rules of quantum mechanics and apply them to gravity. String theory does this. Loop quantum gravity does this. Essentially, every serious program of the last half-century does this, and I want to give the mainstream view its due here, because it is not arbitrary. The reason almost everyone tries to quantize gravity rather than the reverse is that quantum mechanics has never failed. Not once, not anywhere, in 100 years of increasingly vicious experimental scrutiny. General relativity, by contrast, is known to break. Penrose himself proved it breaks, at the singularities inside black holes and at the beginning of the universe. So when you have one theory that provably fails somewhere and another that has never failed anywhere, it is entirely reasonable to assume the second one is the deeper description and the first one is the approximation. That is not laziness. That is the ordinary logic of how physics has always made progress. Penrose's counter is that the two theories fail in different ways. General relativity fails loudly, at identifiable places under conditions nobody has ever been near. Quantum mechanics fails quietly, everywhere, all the time, in the one step it takes every single day and cannot justify. Penrose says the arrow points the other way. His position, argued at length in a paper in Foundations of Physics in 2014 with the title On the Gravitization of Quantum Mechanics, is that the case for gravitizing quantum theory is at least as strong as the case for quantizing gravity. In other words, general relativity is not the theory with the hole in it. Quantum mechanics is, and the missing piece, the thing that says when the second rule applies, is not going to be found by making gravity more quantum. It is going to be found by making quantum mechanics more gravitational. In his 2016 book, Fashion, Faith and Fantasy, in the New Physics of the Universe, he organizes his criticisms of modern theoretical physics into three parts. String theory, he says, is the fashion. Cosmic inflation is the fantasy. And quantum mechanics, the universal, unexamined assumption that the theory is exactly right at every scale forever, is the faith. So, why does he think quantum mechanics is the one that has to bend? The answer is not a piece of quantum mechanics at all. It comes from the other side entirely, from an idea that is 400 years old, and it starts with a man in Italy dropping things off the edge of a table. Part 9. Galileo's falling sphere. Everything that follows rests on one idea, and it is an idea with a beautiful history, and it is not hard. Galileo Galilei established, in the early 1600s, and argued at length in his Two New Sciences of 1638 that all objects fall at the same rate. A heavy stone and a light stone released together hit the ground together. This is not obvious. It is in fact so counterintuitive that it took 2,000 years and a stubborn Italian to nail it down, because everyone's daily experience says otherwise. Leaves drift, stones drop, and it looks for all the world as though heavy things fall faster. Galileo understood exactly why it looks that way. He knew about air resistance. He knew a feather falls slowly because it is being held up by the air and for no other reason. He was extraordinarily insightful about these things, and the distinction he drew between how objects actually behave and how they behave when the air is interfering is one of the founding moves of experimental science. The name for what he found is the universality of free fall, and Penrose has a lovely way of illustrating it, which I should tell you is his own picture rather than anything Galileo wrote. Picture a firework. It climbs, and at the top of its arc it bursts, and the sparks fly outward in every direction at once. Now, the whole spray of sparks is falling. The entire cloud is accelerating downward toward the ground the moment it is born. But watch its shape. The sparks all fall at exactly the same rate, so the shape does not distort. The expanding cloud remains a perfect sphere the whole way down, which means that if you were falling alongside the center of that sphere and you looked at the sparks, you would see them spreading away from you evenly in all directions, with no down at all. In that frame, gravity has simply gone, not weakened, gone. The most famous demonstration of Galileo's principle was not performed in Italy. It was performed on the moon, and it was broadcast live. It is the 2nd of August, 1971. Apollo 15 is at the end of its third and final moonwalk on the Hadley Plain at the foot of the lunar Apennines. The light is flat and merciless. The sun is out and the sky above it is absolutely black, because there is no air to scatter the light into blue. The ground is grey dust that has not been disturbed in 3 billion years, and every footprint the crew has made is still there behind them, perfectly sharp because there is no wind and no water and nothing at all to soften an edge. Commander David Scott stands in front of the television camera. In his right glove he is holding a geological hammer, aluminium, 1.32 kilograms. In his left, pinched carefully, he holds a feather from a falcon, 0.03 kilograms, a hammer and a feather, held at shoulder height, on the moon, in front of several 100 million people. He says more or less that one of the reasons he is standing there at all is a gentleman named Galileo, who made a rather significant discovery a long time ago about falling objects in gravity fields, and then he opens both hands. They do not separate, they do not race. The heavy machined block of aluminium and the vein of a bird go down together side by side at the same unhurried pace, because the moon has 1/6 of Earth's gravity and no air whatsoever, and they arrive in the dust at the same instant, and puff up 2 small clouds that fall straight back down without drifting, because there is nothing to drift in. Scott says, "How about that?" Mr. Galileo was correct in his findings. It is still one of the most watched pieces of archive footage NASA has ever released, and it is one of the very few moments in the history of exploration where a spacecraft was used, essentially, to settle an argument from the 17th century. Now, Einstein. In 1907, working in the patent office in Bern, Albert Einstein had what he later called the happiest thought of his life. He imagined a man falling from a roof, and he realized that during the fall, the man would not feel his own weight. Gravity for that man has been switched off. Not because gravity has stopped acting on him. It is acting on him with its full force, which is precisely why he is falling. But because it is acting on every part of him equally, so there is nothing left over for him to feel. This is not an abstraction. You have experienced it. Every time a lift starts downward too quickly and something in your stomach lifts. Every drop on a roller coaster. Every stumble. That momentary lightness is exactly the erasure Einstein built a universe on, and it is why astronauts on the space station float, not because they have escaped gravity, which at that altitude is nearly as strong as it is on the ground, but because they and the station are falling around the Earth together, and free fall erases weight. But, and this is the crucial qualifier, and Penrose is very precise about it, you can only erase it locally. Falling freely in Pisa gets rid of gravity in Pisa. It does nothing whatsoever about New York. To have a theory in which the freefall frame works everywhere at once, Einstein needed something far more radical, and this is where the picture becomes geometry. If every falling observer is entitled to say that gravity has vanished for them, and different falling observers are falling in different directions, then the only way to reconcile all of them is to abandon flat space entirely. Space-time has to bend. That is general relativity. Gravity is not a force that pulls. Nothing in free fall is being pushed or pulled at all. Everything in free fall is going as straight as it possibly can, and space itself is what is curved. The moon is not on a leash. It is going straight, through a geometry that Earth has bent into a valley. The technical version of the idea has a name, the strong equivalence principle, and it says something quite strong indeed. It says that locally, inside a freely falling frame, the laws of physics take exactly the form they would take if there were no gravity at all. Not approximately, not for practical purposes. Gravity is not merely hard to detect in a falling frame, it is undetectable in principle, because there is nothing there to detect. The freefall frame is not one convenient point of view among many. In general relativity, it is the privileged one. It is what the theory means by standing still. That deserves a moment, because it is the deepest and strangest thing Einstein ever said. Every other force in nature can be shielded or screened or measured against a background. You can put a charge in a metal box and the electric field outside stops existing for it. Gravity has no box. It acts on everything, in proportion to exactly the thing that resists acceleration, which is why it can be transformed away completely by the simple act of letting go. That total, unshieldable universality is going to become important in about 10 minutes, because if you were looking for one interaction in nature capable of doing something to every particle in existence with no exceptions, there is precisely one candidate. The word physicists use for the straightest available path through a curved geometry is geodesic, and it is worth having, because it removes the last trace of pulling from the picture. On the surface of the Earth, the straightest line between London and New York is not the one that looks straight on a flat map. It is the great circle that arcs north over Greenland. It looks curved only because you drew it on the wrong kind of paper. In general relativity, every falling object is doing the same thing. The apple is not being tugged. The apple is going straight. Straight in the neighbourhood of a planet just happens to lead down. Penrose has said, and I like him for saying it, that some of the arguments Einstein used to get himself there were not actually correct. That the business with the rotating disk, for instance, does not really work when you look at it closely. And the conclusion was exactly right anyway. Einstein saw that he needed a non-flat geometry before he could fully justify why, and Penrose has admitted he does not entirely understand where that insight came from. The result has been tested to a precision that is hard to overstate. The Microscope satellite mission reported in 2022 that two test masses of different composition fall at the same rate to about 1 part in 1,000 million. General relativity is now confirmed to a level comparable with quantum mechanics itself, and that is exactly the problem. Because we now have two theories, both tested to extraordinary precision, both apparently exactly true, neither of which can be dismissed as a rough approximation to the other. And Roger Penrose is about to take one lump of matter, put it in two places at once, and show you that they cannot both be exactly true about it at the same time. Part 10. Two spacetimes. Here is the argument. I am going to build it one step at a time, and none of the steps is difficult, and at the end of it you will be holding one of the most interesting ideas in modern physics. Take a lump of matter. Any lump, a speck of dust, a grain of sand, it does not matter yet, and put it into a superposition of two positions, over here and over there, both at once. Quantum mechanics says you may do this. More than that, quantum mechanics insists on it. We established this back at the beginning. The Schrödinger equation is linear, and linearity means that if the equation permits the lump here and permits the lump there, then the sum of those two states is also a permitted state of the world. There is nothing exotic about the request. It is the most ordinary thing the theory does. Now bring general relativity into the room. General relativity says that mass curves spacetime. The lump sitting over here bends the geometry around it into a particular shape, a valley in the fabric, deepest at the lump's location, and the lump sitting over there bends the geometry into a different shape, with the valley in a different place. So look at what you actually have. In the first branch of your superposition, spacetime has one shape. In the second branch, spacetime has a different shape. You do not have one spacetime containing a lump that is in two places. You have a superposition of two different spacetimes. Say that to yourself once more, slowly, because everything follows from it. Two geometries, two shapes of the fabric, both present, both real, superposed in the way quantum mechanics superposes things. And now try to write down the Schrödinger equation for that state. Here is why you cannot. In order to say how something evolves in time, you need a notion of time, and specifically, you need what physicists call a time translation operator. It is a rule that takes the state now and shifts it forward by 1 instant. and to build such a rule, you have to be able to say what the same place one moment later means. You need to be able to point at a location in your geometry, wait, and point at the same location again. In a single spacetime, that is straightforward. In a superposition of two spacetimes, it is not, because there is no natural, unambiguous way to say which point in the first geometry corresponds to which point in the second. They are different shapes. There is no dictionary between them that the physics singles out as correct. And this is exactly where the equivalence principle comes in, and why we spent the last part with Galileo and a falling hammer. The equivalence principle says the freefall frame is the privileged local frame, that freefall is what the theory means by standing still. But each of the two geometries in your superposition has its own family of freefall frames, and those families are genuinely different. A particle falling freely in branch 1 is not falling freely in branch 2. There is no shared notion of standing still, and the equivalence principle is not a technicality you can quietly drop while you sort out the mathematics. It is the foundation the entire theory of gravity is built on. Penrose expresses the same problem in the language of vacua, which is worth hearing because it is more precise. Each of the two spacetimes defines its own vacuum, its own answer to the question of what it means for nothing to be happening, and the two answers are inequivalent. Without a shared notion of stationarity, there is no well-defined time translation, and without a well-defined time translation, by a chain of reasoning that runs straight through the deepest connection in physics between symmetry and conservation, there is no well-defined energy. That is the crux. The superposed state has an intrinsic, irreducible uncertainty in its energy, and this is not an experimental limitation, not a shortcoming of anyone's instrument, not a statement about what you can know. It is a statement about what there is. The geometry itself cannot say what the energy of that state is, because the geometry cannot decide what standing still means. And now the loose end I left dangling in the last part comes back and ties itself off. I said that gravity is the only interaction in nature that cannot be shielded, that it acts on everything, without exception, in proportion to the very property that resists acceleration. If you were shopping for a mechanism capable of enforcing definiteness on every particle in the universe with no exemptions, you would need something that touches everything, everywhere, always, with no way to hide from it and no neutral particles that ignore it. Electromagnetism will not do. Half of matter is neutral. The nuclear forces will not do. They do not reach past an atomic nucleus. There is exactly one candidate on the list, and it is the one nobody wanted to put there. Penrose then does something that turns this from a philosophical objection into physics. He quantifies it. The relevant quantity, which he writes as E sub g, is the gravitational self-energy of the difference between the two mass distributions, which sounds forbidding, and is actually simple. Take the mass distribution in branch 1, subtract the mass distribution in branch 2. You're left with a kind of ghost object, mass in one place, negative mass in the other. Now compute how much gravitational energy that ghost would have, using nothing more exotic than Newton's law. That number is E sub g. It grows when the lump is heavier, and it grows when the two positions are further apart. It measures, in a single figure, how badly the two geometries disagree. And then the last step, which is the one I find genuinely beautiful. In quantum mechanics, there is a relationship between energy uncertainty and time, and it shows up most familiarly in unstable particles. A particle that decays quickly does not have a sharply defined energy. Its energy is smeared out, and the faster it decays, the more smeared it is. The relationship is that the lifetime is roughly Planck's constant divided by the energy width. Physicists use it every day, in reverse, to work out particle lifetimes from the widths of peaks in their data. Penrose runs it in the other direction. If a superposed state has an intrinsic energy uncertainty of E sub g, then that state cannot persist indefinitely. It has a lifetime, and that lifetime is roughly Planck's constant divided by E sub g. Tau equals h bar over E sub g. That is the formula. It is in a paper called On Gravity's Role in Quantum State Reduction, published in the journal General Relativity and Gravitation, Volume 28, pages 581 to 600 in 1996. And what it says is this: a superposition has a shelf life, not because anyone looked at it, not because it became complicated, not because it got entangled with the air, though it will do that too and far faster, because the geometry underneath it cannot hold two shapes indefinitely, and the more strongly the two shapes disagree, the sooner one of them has to go. Now I have to tell you what this argument is not. because Penrose is scrupulous about it, and any honest account has to be. It is not a theory. He says so himself, repeatedly and without hedging. There is no complete set of equations here. Nothing you could hand to a graduate student and say, calculate. What he has is an argument that the standard framework contains an inconsistency and a heuristic estimate of the scale at which that inconsistency should start to bite. It is a prediction of when, not a mechanism for how. The full theory does not exist, and he is 94 years old, and he knows perfectly well he may not see it. Nor does it explain everything you would want explained. The most serious gap is the Born rule. The formula tells you that a superposition must end after a certain time. It does not tell you why the probability of each outcome is the square of its amplitude, why 60-40 rather than 50-50. That number is still coming in from outside as an extra ingredient exactly as it does in the textbook. Penrose acknowledges this is unfinished business, and there is a third difficulty which is arguably the sharpest. Collapse in this picture is an objective physical event. It happens somewhere, at some moment. But at some moment is not a frame-independent notion in relativity. Two observers moving relative to one another disagree about which events are simultaneous. Building a version of this idea that is fully compatible with special relativity is a genuine open research problem, and it is one of the strongest technical objections anyone raises against the entire program. So the honest summary is that this is not a finished replacement for quantum mechanics. It is a well-motivated suspicion with one number attached to it. I want you to sit with the shape of that idea for a moment, because it reverses something. For 90 years, the collapse of the wave function has looked like the place where physics runs out. The embarrassing step, the hand wave, the thing you do when the equations stop helping you. In this picture, it is not where physics runs out, it is where a different piece of physics takes over. The reason the world is definite is not that somebody is watching it. The reason the world is definite is that space-time is not built to hold two answers at once, and there is a limit, a real, physical, calculable limit to how much room the universe has for indecision. And notice what has disappeared from the story. There is no observer in it. There is no mind, no consciousness, no measurement, no apparatus, no cut, no chain, no physicist making a judgment call. Penrose has said this in interview after interview, and it is constantly misreported, so let me be as plain as he is. In his picture, collapse is a physical process that would go on exactly the same way in a universe with nobody in it at all. There is one more thing worth saying about why this proposal deserves your attention, where the interpretations did not, and it is the simplest thing in the whole video. Many worlds cannot be wrong. Pilot wave cannot be wrong. The relational and observer-centered views cannot be wrong, not because they are correct, but because every one of them predicts exactly what the textbook predicts, forever, in every possible experiment. They are unfalsifiable by construction. This one is not. This one changes the equation, which means it changes the predictions, which means somebody can go into a laboratory and kill it. But here is what makes it more than a nice story. Tau equals h bar over E sub g is not a sentiment. It is an equation with numbers in it, and numbers can be checked. Part 11. How long a grain of sand can be in two places. So let us put some numbers in. Start at the bottom. Take a single proton and put it into a superposition of two positions separated by roughly its own width, about a millionth of a billionth of a meter. Work out the gravitational self-energy of that difference. A proton has a mass of about 1.67 times 10 to the minus 27 kilograms, and gravity is by an enormous margin the feeblest of the forces, so E sub g comes out absurdly, almost comically small, and since the lifetime is Planck's constant divided by that number, the lifetime comes out enormous. Depending on exactly how you set up the calculation, you get something in the range of millions of years and upward. For an electron, which is nearly 2,000 times lighter still, you get a lifetime longer than the current age of the universe. Now, that might sound like the theory failing. It is the opposite. It is the theory doing the single most important thing any new proposal has to do, which is to reproduce everything we already know. Quantum mechanics works flawlessly for particles. Any modification to it that made particles collapse quickly would have been dead on arrival, contradicted by every experiment ever done with an electron. In Penrose's picture, the mechanism is there for a proton, and it is so slow as to be completely irrelevant, and that is exactly as it must be. But now scale up. And this is where it gets interesting, because gravitational self-energy does not creep upward as things get bigger, it climbs steeply. Double the mass, and you do considerably worse than double E sub g, because both the mass doing the pulling and the mass being pulled have gone up, which means the lifetime does not decline gently, it falls off a cliff. So the obvious question is, where is the cliff edge? And to answer that, we need to talk about a number that has been sitting quietly in physics for well over a century, being strange, and that almost nobody outside the field ever thinks about. In 1899, Max Planck noticed that if you take the three most fundamental constants in nature, the gravitational constant, which sets the strength of gravity, the speed of light, which sets the structure of space-time, and the quantum of action that now bears his name, which sets the graininess of quantum mechanics, you can combine them in exactly one way each to produce a length, a time, and a mass. These are not human units. They do not depend on the Earth, or on the meter, or on anyone's arm. They are the units the universe would use. The Planck length comes out at about 10 to the minus 35 meters. That is roughly 100 million times smaller than a proton. It is so far beyond any conceivable experiment that we may never touch it. The Planck time is about 10 to the minus 43 seconds. It is the time light takes to cross a Planck length. It is, by a very wide margin, the shortest interval anyone has ever had reason to name. And then there is the Planck mass. 2.176 times 10 to the minus 8 kilograms, which is 21.76 micrograms. I want to make sure that lands, because on a list of numbers it disappears. The Planck length is unimaginably small, the Planck time is unimaginably small, and the Planck mass is a grain of sand. Not a metaphorical grain of sand, a literal one. 21 micrograms is roughly a fine grain of beach sand, about 1/3 of a millimeter across, sitting on your fingertip. You could see it. You could feel it if you concentrated. Penrose likes to describe it as about the mass of a flea's eye, which is a wonderful image and is probably a slight underestimate. A flea's egg or a small sand grain is closer. Either way, it is an object from the ordinary world. Nobody knows why. Every other quantity built from the fundamental constants is remote beyond reach, and this one landed on the kitchen table. It is one of the genuinely odd facts about our universe that essentially never gets mentioned, and it has been sitting there since 1899 waiting for somebody to find a use for it. Penrose found one, because when you take an object of roughly the Planck mass and you put it into a superposition of two positions separated by about its own size, and you compute E sub g and you divide Planck's constant by it, you get about 1 second. Hold out your hand. Imagine a single grain of fine sand sitting on your open palm. Now imagine that grain lifted gently into a superposition of two positions a hair's breadth apart. Over here and over there, in the way an electron is in two places in the double slit, except that this is not an electron. It is a thing you can see. In standard quantum mechanics, nothing whatsoever forces that state to end. Keep the grain cold, keep it dark, keep every stray photon and air molecule away from it, which is impossible in practice, but the theory does not care about practice. In principle, that grain stays in two places forever. There is no term anywhere in the Schrödinger equation that grows tired. In Penrose's picture, there is a clock running, and the clock is not measuring anything the grain is doing. The grain is not decaying. The grain is not interacting with anything. What is being measured is how long the geometry underneath the grain can hold two shapes without one of them having to give way. About a second. Sit inside that second with me. Nothing observes the grain. Nothing measures it. No apparatus, no physicist, no mind, no consciousness. It simply sits there, in two places, in the dark, and the universe holds both possibilities open and then quietly runs out of room, and the grain is somewhere. That is what Penrose is proposing. That the definiteness of everything you have ever encountered is that process, happening constantly, everywhere, at speeds far too fast to notice, because everything you have ever encountered is astronomically heavier than a grain of sand. It is worth filling in the middle of that scale, because the collapse from hours to instants happens over a surprisingly narrow range. In his 1996 paper, Penrose works through a small sphere about a 10,000th of a centimetre across, and finds lifetimes running from hours at the bottom of the range down to fractions of a second as the object grows, an entire span from a working afternoon to a blink, across a change in size you would struggle to see under a decent microscope. Go up to anything you could hold between two fingers, and the predicted lifetime becomes so short that no instrument anyone has proposed could resolve it. Which is again exactly what the theory needs. If it predicted that a coin could stay in two places for a measurable fraction of a second, we would have noticed by now. And there is a second way to test the whole idea, which does not involve looking for radiation at all. Build a superposition heavy enough and separated enough that the formula says it should collapse in, say, 1/10 of a second. Then hold it for a second and see whether the interference is still there. If the fringes fade on schedule, Penrose is right. If they survive, he is wrong. That experiment requires a mass and a separation nobody can currently reach. But the gap has been closing at roughly an order of magnitude a decade, and there are groups building toward it now. Now, one more thing about that formula, and it is the part that makes physicists sit up. Penrose was not the first person to write it down. A Hungarian physicist named Lajos Diossi got there earlier, and by an entirely different road. He published a paper in Physics Letters A in 1984 on gravitation, and the quantum mechanical localization of large objects, followed it with a paper in the same journal in 1987, proposing what he called a universal master equation for the gravitational violation of quantum mechanics, and completed the picture in Physical Review A in 1989. His motivation had nothing to do with the equivalence principle, or with vacua, or with any of the geometric reasoning we just walked through. He was working on a much more technical problem. How do you couple quantum matter to a classical gravitational field without the whole thing producing nonsense? And when he pushed that problem hard enough, out came a collapse mechanism with a characteristic decay time, essentially the same decay time. Penrose has been candid about this. He did not know about Diossi's work when he did his own. He has said that Diossi's argument was not his argument, that as far as he could tell it was not a gravitational field argument in the sense he meant, and that he was rather surprised to discover it had already been done, roughly 2 years before him. Two people, incompatible starting points. One from the geometry of space-time and the failure of the equivalence principle under superposition, the other from the technical demands of coupling quantum matter to a classical field, converging on the same number. That is the kind of coincidence that makes physicists pay attention, because formulas that fall out of two unrelated arguments have a habit of turning out to be about something real. Ever since, the model has carried both names, the Diossi-Penrose model, and now, finally, remember that number I asked you to hold on to about an hour ago? The sapphire crystal in Zurich, ringing in a superposition of two opposite phases with an effective mass of 16 micrograms. The Planck mass is 21.76 micrograms. We are within a factor of 1.5. I have to be honest about what that does and does not mean, because it is easy to overstate. A sub-G depends on the separation as well as the mass, and the separation in that sapphire experiment is still minuscule. The two superposed states are two phases of a vibration, not two locations on a bench. In the dimension that matters most, we are still a very long way off, but in raw mass, humanity has now built a quantum superposition of an object that weighs roughly 2/3 of the deepest mass scale in physics. 50 years ago, that sentence would have been science fiction, which brings us all the way back to a mountain in Italy. Because a formula with numbers in it is a formula you can go and check, and for the last 2 decades, that is exactly what people have been doing, sitting in the dark under 1.5 kilometers of rock listening. Part 12. The Glow Explained. At the very beginning of tonight, I told you about a machine under a mountain, listening for a faint X-ray whisper coming from cold, undisturbed matter. It is time to explain why anybody thought that whisper might be there. The reasoning is short, and it is the hinge of every experiment in this field. If the wave function really does collapse spontaneously, if there is a genuine physical process constantly nudging things toward being in one place rather than several, then that process is not gentle, and it is not selective. It is acting on every particle in every atom in the universe, all the time, forever. And most of those particles carry electric charge. Protons carry it, electrons carry it, and a jostled charge radiates. That is not a subtle prediction. It is the operating principle of every radio transmitter ever built. Shake an electron, and it throws off electromagnetic waves. So if reality is being continually and randomly localized, then all ordinary matter, the xenon in the tank, the rock overhead, the chair you're sitting in, should be emitting a very faint, very steady drizzle of X-rays, for no reason, from nothing, permanently. Standard quantum mechanics predicts precisely zero. Collapse models predict something, and that difference is the whole reason this corner of the argument escaped from philosophy and got into a laboratory. There is one complication that you need in order to follow what happens next, and it is a parameter. The simplest version of the model, taken literally, predicts an infinite amount of energy production, which is obviously wrong. The standard fix is to introduce a short-distance smoothing length, usually written R0, which effectively says that the model stops behaving that way below a certain scale. Think of it as the size of the fuzzy blob the theory uses instead of a point when it works out the gravitational self-energy of a nucleus. And here is the key relationship. The smaller R0 is, the more violently the model localizes things, and the more radiation it predicts. So if you go looking for the radiation, and you do not find it, what you have measured is a lower limit on R0. The most beautiful version of the theory is the one where you do not get to choose. Set R0 at the size of an atomic nucleus, about 10 to the minus 15 meters, the natural scale, the one nature already provides, and the model has no adjustable knobs whatsoever. It predicts a specific rate of collapse and a specific amount of radiation with nothing left to tune. That is the version physicists find attractive, because a theory with no free parameters is a theory that cannot wriggle. In 2020, that version died. A team consisting of Sandro Donardi, Cristian Pisciccia, Catalina Curcianu, Lajos Diossi, Matthias Laubenstein and Angelo Bassi ran a dedicated germanium detector far beneath the Gran Sasso mountain and published the result in Nature Physics, Volume 17, pages 74 to 78, in a paper titled Underground Test of Gravity-Related Wave Function Collapse. Their conclusion, in their own careful words, was that the result sets a lower bound on the effective size of the mass density of nuclei, about 3 orders of magnitude larger than previous bounds, and that this rules out the natural parameter-free version of the Diossi-Penrose model. Look at that author list again. Lajos Diossi is on the paper that killed the cleanest form of his own model. He did not write a rebuttal. He did not sit it out. He helped build the experiment that constrained the idea he had spent 30 years developing, and he put his name on the result. There are not many fields where that happens, and there is something in it that I find genuinely moving. This is what the thing is supposed to look like when it is working. It is worth appreciating how far this has come. Before Gran Sasso, the best bounds came from earlier germanium searches, and put R0 somewhere above about half of 1/10 of a nanometer, a limit that still left the parameter-free version comfortably alive. Within about a decade, that number has been pushed up by more than 3 orders of magnitude, and the elegant theory has gone from viable to dead. There is no drama in the papers. Nobody announced anything. It happened in the way most of physics actually happens, which is quietly, in tables of upper limits, over years. 2 years later, another underground germanium experiment, the Majorana demonstrator, tightened the screw again, reporting in physical review letters a bound pushing the Diossi-Penrose length above about 2.54 times 10 to the minus 10 meters at 95% confidence, 2.5 angstroms, comparable to the width of an atom and 5 orders of magnitude above the nuclear scale the elegant version had required. And then we come back to where we started. Picture it. You drive into a tunnel through a mountain in the Abruzzo, and halfway along you turn off through a set of doors into a cavern the size of a cathedral, carved out of the rock in the 1980s for exactly this purpose. Inside it there are experiments in every direction, most of them looking for things that may not exist. And in one of the halls there is a tank, 8.5 tons of xenon, held as a liquid at around 177 degrees below zero, purified until the radioactive contamination is measured in parts per trillion, because a single stray atom of the wrong isotope would drown the signal. 494 photomultiplier tubes above and below, each capable of registering a single photon, all of them staring inward into total darkness. Around it, water. Around that, rock. 1,400 meters of it, 3,600 meters of water equivalent, keeping out the constant rain of cosmic rays that falls on the rest of the world, and then waiting. From the 6th of July to the 10th of November, 2021, that machine sat in the dark and counted. 1.16 ton-years of exposure. 4 months in which the most sensitive parts of the apparatus recorded a background of about 15.8 events per ton per year per kilo electron volt, which is to say, almost nothing, which is the entire achievement. and what it was listening for was not a particle from space. It was listening for the sound of reality making up its mind. A faint X-ray hiss that would only be there at all if the wave function collapses on its own, without anyone watching, everywhere, all the time. There was no hiss. The result was published on the 23rd of March 2026 in Physical Review Letters, Volume 136, Article 120201. The analysis did something nobody had done before. It properly accounted for the fact that protons and electrons carry opposite charges, so their collapse-induced emissions partially cancel each other out, which changes the shape of the expected spectrum. Getting that right is what sharpened the result. The Diossi-Penrose bound improved by roughly a factor of 5, and the other great family of collapse models, continuous spontaneous localization, which descends from a 1986 proposal by Ghirardi, Rimini and Weber, and is not gravitational at all, but simply posits random localizations at a fixed rate, that bound improved by 2 orders of magnitude, which was enough to do something that had never been done. The parameter values that Ghirardi, Rimini and Weber themselves proposed in 1986 as their best estimate of how the universe actually works are now experimentally excluded. An entire generation's default guess about the underlying structure of reality off the table because of 4 months of silence under a mountain. And there is one more squeeze which is quieter and in some ways worse. Everything I have described pushes R naught upward from below. You cannot make it too small, or you would see the glow. In 2024, a group including Bassi and Donardi asked the opposite question, and published it in New Journal of Physics under the title On the Effectiveness of the Collapse in the Diossi-Penrose Model. Their point was this: if R naught is too large, the collapse becomes too weak and too slow to actually do its job, to actually make large objects behave classically, which is the entire reason the model was invented in the first place. What they found is unwelcome. The collapse rate does not simply grow with mass the way you would hope. It saturates as systems get bigger, and it depends on the shape of the object, whether it is a cube or a flat plate. And their conclusion, stated flatly in the abstract, is that not all macroscopic systems collapse effectively. The rough upper limit they extract with acknowledged arbitrariness sits around 1/10 of a millimetre. I should add, in fairness, that killing one member of a family is not the same as killing the family. All of these models predict something else besides radiation. Because random localization injects energy into matter, they all predict that isolated objects should very slowly warm up for no reason. Nobody has ever seen that heating either, and it provides an entirely independent line of attack. And it is also the reason theorists have built variants with dissipation built in, and variants driven by coloured rather than white noise, specifically designed to tame the energy problem. Some of those survive constraints that the simplest versions do not. Some of the tightest limits of all come from astrophysics, rather than from any laboratory, because over cosmological timescales, even an absurdly slow heating has consequences you could see. The picture is not one theory being executed, it is a family being pruned. So the surviving window for this parameter now runs from a few angstroms at the bottom to something like 1/10 of a millimetre at the top. And inside part of that range, the model fails to deliver the very thing it was built to deliver. The room is not empty, but it is a corridor now, and it is being walked from both ends by the same handful of people who keep working on it anyway. That is where the physics stands tonight, and it is everything we need to finally answer the question this video opened with. Part 13. Why they look away. So, why do most physicists ignore quantum mechanics' biggest flaw? I promised you a straight answer, and here it is, in parts, because there is not one reason. There are 5 good ones and 1 bad one, and I want to give you all 6, honestly. The first reason is the simplest, and it is the one people find hardest to accept because it is so unglamorous. The recipe works. Not approximately, not well enough. 12 decimal places. The 2-rule procedure, whole and all, correctly predicts the magnetic moment of the electron to a precision that is difficult to find analogies for. It correctly describes every semiconductor in every device you own. It runs the lasers in your fibre optic cables and the magnets in every hospital scanner. In 100 years of use by millions of people, applying the collapse postulate by hand at whatever moment seemed convenient has never once given a wrong answer. A physicist's week consists of problems that can be solved, and there is not a single problem on that list whose solution requires knowing what a measurement is. Careers are short. The work is hard. That is not evasion. That is triage. The second reason is cultural, and it has a name. It is sometimes called the shut up and calculate school, and it is usually presented as a criticism, but its history is more sympathetic than that. After the Second World War, physics went from a small European conversation to an enormous, well-funded, industrialized enterprise, and the young field of particle physics was producing results at a ferocious pace using a theory nobody could interpret. The people asking about foundations were, quite visibly, not the people producing results. A norm formed that foundations are what you do after you retire, and norms like that are transmitted by supervisors to students, silently, in the choice of which questions get encouraged. It is worth remembering that D to Z's career was damaged for asking, and that Hugh Everett left academic physics entirely after his interpretation was received badly, and never came back. This is not a field that has historically rewarded curiosity about its own foundations. The third reason is decoherence, and we spent a long time on it because it is the load-bearing one. Decoherence gave the community a story that is true, quantitative, experimentally confirmed, and good enough to stop the question. And seeing what it leaves out requires holding on to a distinction, proper mixture versus improper mixture, that sounds like philosophy, reads like philosophy, and can therefore be filed as optional by anyone who has a grant to write. The hole did not get filled, it got covered with something you can stand on. The fourth reason is that every alternative costs something, and physicists can read a price tag, run the ledger. Copenhagen makes the theory work by requiring part of the universe, the part with the instruments in it, to sit outside the theory and be described in different language. Many Worlds removes the second rule entirely, at the cost of every outcome that did not happen to you having happened to someone identical to you, forever, in numbers beyond counting. The pilot wave picture gives you determinism and definite positions at the cost of explicit non-locality and an uncomfortable relationship with relativity. Relational and observer-centered views dissolve the problem by making facts relative to observers, which means giving up the idea of one shared set of events. And objective collapse, the one we have spent tonight on, pays by modifying the most successful equation in science, and then has to explain why the modification has stayed hidden from every experiment ever performed while still being strong enough to do its job. Every door has a toll. When every door has a toll, the cheapest thing to do is stay in the corridor. That is not cowardice. That is economics. And the fifth reason is the one that actually mattered most, and it is the one I want you to hold on to. Until very recently, there was nothing to measure. Every one of those positions I just listed, with the single exception of collapse models, makes exactly the same predictions as the textbook. Identical in every experiment to every decimal place, forever. Which means choosing between them is a matter of taste. And physicists are trained, correctly, to be impatient with matters of taste, because the entire method of the discipline is built on the idea that nature settles arguments and people do not. Telling a working physicist that they should spend their career on a question no experiment can decide is telling them to stop being a physicist. That is the honest answer. 5 good reasons, and every one of them is a reason I would probably have accepted myself. But look at what has happened while nobody was paying attention. That 5th reason has expired. There are now numbers, real ones, published in Nature Physics, in physical review letters, in New Journal of Physics, with error bars and confidence levels that make a position about the nature of reality wrong. The parameter-free Diossi-Penrose model is dead, killed under a mountain, with its own inventor as co-author. The original Ghirardi-Rimini-Weber parameters are excluded. The surviving window has been squeezed from below by 4 months of silence in a xenon tank, and from above by the requirement that the theory still do its job. This is no longer a matter of taste. It is a measurement, and it is being taken. Now the 6th reason, the bad one. A significant number of physicists dismiss gravitational collapse without examining it, because they associate it with quantum consciousness. And I want to walk through that carefully, because it is the least comfortable part of tonight, and it deserves accuracy rather than a wave of the hand. You will have met the claim that consciousness collapses the wave function, that reality stays a fog of possibility until a mind observes it, and that the double-slit experiment proves it. It is everywhere online, and it did not come from nowhere. It came from Eugene Wigner, a Nobel laureate, who followed von Neumann's chain to the end in the 1960s, and concluded that the only candidate he could find for terminating it was consciousness itself. That is a serious pedigree. It is also not supported. The witch path information in a double-slit experiment is destroyed by the apparatus, not by anyone's attention. The interference vanishes whether or not a human being ever reads the detector output, and decoherence supplies a complete quantitative account of why, involving no minds anywhere. Wigner abandoned the position himself, in part because of where it leads. If only conscious observation makes things definite, then whose and what exactly was the universe doing for the 13 billion years before there was anybody in it? The sophisticated version is called orchestrated objective reduction, and it is Penrose's, with the anesthesiologist Stuart Hameroff, from the early 1990s. It grew out of that 1989 book I mentioned, the argument that human mathematical insight is non-computable, and that therefore the brain must be doing something that is not classical computation. Hameroff proposed a substrate, microtubules, the protein scaffolding inside neurons. The proposal is that quantum coherence in those structures is terminated by the same gravitational reduction on the same tau equals h bar over E sub g timescale, tuned to land at somewhere between 25 and 40 milliseconds, the rhythm of conscious moments. Its status is this. In 2000, Max Tegmark published a calculation in Physical Review E, arguing that a warm, wet, noisy brain decoheres in something like 10 to the minus 13 seconds or faster, against cognitive timescales of milliseconds, a gap of 10 orders of magnitude or more, which would make the whole thing impossible. In 2002, Hagen, Hameroff and Tuzinski replied in the same journal, arguing that Tegmark had used the wrong separation and the wrong assumptions about the surrounding material, and that corrected values buy back around 7 orders of magnitude. That is a real rebuttal. It also still leaves the theory 2 or 3 orders short of what it needs. The gap is disputed, not closed. Then, in 2022, a group including Diossi, Laubenstein, Pischikia and Curcianu used the Gran Sasso radiation bounds to argue in Physics of Life reviews that a version of the theory built on the simplest gravity-related collapse is highly implausible, though they noted that more complex variants leave room. And in 2024, a laboratory at Wellesley College published in a Neuro a result showing that rats pre-treated with a microtubule stabilizing drug took significantly longer to lose consciousness under anesthesia. That is genuine evidence that microtubules are involved in how anesthetics work. It is not evidence of quantum coherence in the brain, and I want to be very clear that those two things are not the same, because they get blurred constantly. So here is the cost, and it is heavy. One of the very few testable ideas in the foundations of quantum mechanics, perhaps the only one, has spent 30 years carrying reputational baggage from an application to consciousness that its own author published in a separate book, that most physicists find implausible, and that has nothing logically to do with whether space-time can hold 2 shapes at once. Penrose has said, over and over, in interview after interview, that his collapse mechanism has nothing to do with observers or minds, that it would happen exactly the same way in a universe with nobody in it. It has not helped. Mention gravitational collapse in a physics department, and a certain number of people stop listening at the word gravitational. So there is the full answer. 5 good reasons, 1 bad one, and 4 of the 5 have quietly stopped applying. They are not ignoring it because they are dishonest or incurious or hiding something. They are ignoring it because it did not pay, because the alternative explanations were excellent, because the alternatives to the alternatives were untestable, and because the one testable option arrived wearing the wrong clothes. Every one of those is a human reason, and I do not think any less of anyone for it. But the second rule is still there. It has been sitting on the second page of the textbook since 1926. The rule with no equation, applied by hand, at a moment nobody can specify. It is not really a defect in the theory. It is more like a place where the theory stops and the world keeps going, and somebody eventually has to walk out into the gap and see what is there. And I will leave you with the thing that I cannot stop turning over. Of everything we have talked about tonight, the geometry, the mountain, the sapphire crystal ringing in a fridge in Switzerland, the grain of sand held in 2 places, the strangest item is not on that list. The strangest item is the most ordinary experience you have ever had. The fact that things are simply one way, that the cup is on the table and not also on the floor, that you are here, in one place, at this moment, listening to this, and not also somewhere else listening to something different. You have never once, in your entire life, had to wonder about that. It is the most reliable feature of being alive, and it is, as far as anyone can tell, the single least explained phenomenon in physics. If Penrose is right, the reason is not that anyone is watching. The reason is that the universe has only so much room for indecision, that space-time cannot hold two shapes at once for very long, and the heavier the disagreement, the sooner it has to end, and that everything definite you have ever encountered is what it looks like when that room runs out. Nobody knows whether he is right. The corridor is narrowing. It may close entirely in the next 20 years, and if it does, it will close because people kept sitting in the dark under a mountain, counting almost nothing, for months at a time. That is not a flaw being ignored, not anymore. That is the last honest question at the bottom of physics, finally getting asked out loud, and it turns out the answer, if it comes, will not come from an argument. It will come from a machine, in a very quiet room, listening for the sound the universe makes when it decides.